Hello guys, in this video we will first remember question 1 from previous video and explain what kind of problems will occur if we decide to solve the same problem with new data. And as a second part we will learn to separate the data and model for problem 1 and rewrite the GLPK code and solve it again. And after this we will make minor changes in our code and we will split the data and model to different files. And as a last part, we will demonstrate the benefits of data model separation by adding new data and resolving the problem. And in the next video, we'll talk about minimization of the cost by giving example of diet problem. Let's start by remembering the question from previous lesson. We have a steel production factory and we have two products. Profit value for steel bands is $25. Time to create 1 ton of steel bands is 1 divided by 200 hours, and maximum limitation per week for steel bands is 6,000 pieces. And for steel coils, profit per 1 ton is $30. Time per 1 ton is 1 divided by 140 hours. And maximum limitation per week is 4,000 pieces. And in our factory, available production time for week is limited by 40 hours. The question we are trying to solve is how many bands and coils should be produced for maximum profit. And in the previous video, because our question was really simple, we created a solution in a simplest possible way using GLPK. But this kind of approach has some major problems. And now, before improving our code, I want to talk about what are these problems. Let's look at our previous code and let's imagine what would happen if we had 100 products instead of 2. First of all, we will need to manually add 100 variables here. Also, we will need to update our goal equation for each product with variables and corresponding parameters. And we will need to update our total time per week constraint equation, and for each product we will also need to add a new constraint equation about their upper limits. And as you can understand, it's not really feasible because every time we are adding new data, although we are solving the same problem, we have to update our model code, and we don't want this. As a solution to this problem, in this video we will learn to separate our solution in two parts. And first part will be our model part, where we use a generalized model of question, and second part will be our data part. By doing that, to solve different instances of the same problem, changing the data part will be sufficient. So let's create a new file. In GLPK, model and data partition is implemented in certain order. First, we model our data, and then if we have any display code, we will type them. And then we will tell GLPK to solve the equation, and we will put our data. And as a last part, we will tell GLPK we end our code. Now we can start to code our model part of the solution. When we are trying to convert or code from scratch the generalized model, there are two main rules we need to consider. Our first rule is model part shouldn't include any data. And our second rule is model should be flexible and allow arbitrary number of variables. If you look at our last code, in our factory we had only two products, XB and XC. And in this code, as you can see, we are implementing them one by one manually, which is against our second rule that model should be flexible and allow arbitrary number of variables. We can overcome this by telling GLPK we have a set of products and we don't know how many products we have in the set. So let's create a set and let's call it products. And details of this definition will be pulled from data section. We don't need to provide any more information. It can have 1 element or 1,000 elements. We don't know it. It will be implemented inside the data part of the code. And if you continue, we need to implement one variable for each product, which corresponds to the amount should be produced for maximum profit. To do that, we will simply create a variable x and tell GLPK this x variable has different value for each element of our set of products. And indexing between the elements will be done by j. This simply shows us that x square brackets 1 is a variable which shows us how much we should produce from the first element of our set for maximum profit. And there will be same amount of x's as the products in our set products. And in our last solution, as you can see here, we have some hard-coded values. And this is against rule number 1. We can overcome this problem by converting our values to parameters. We can just create a parameter called profit per ton, but this parameter will hold only one value. And what we want is that it must hold value for each product we have in our product set. To make this happen, we will simply do the same thing we did in our x variable, and like that. And now it will act like a list of values, and it will hold independent values for each product we have. And if you look at our last code, you will see a bunch of other values. These values are about how many tons we can produce per hour, and these values are about upper limits of each product. So let's convert them to parameters. We can add this here because we will have this parameter for each product. And we can do the same thing here, and we can call upper limits. And here you will see one last number. This number is available production time in our factory per week. This parameter doesn't change with each product, so we don't need to add the indexing part like we did with other parameters. And after creating our variables and parameters, now we can create our goal equation. Previously, to calculate goal equation, we simply multiplied each product profit by the amount of that product and take the summation of these results. Mathematical notation of what we are trying to do is this. For each element of our set of products, we multiply profit per ton of that product with the amount to be produced. And after that, we make a summation of all these results, and this will give us the total profit. And the power of AMPL language and GLPK is that we can easily implement these mathematical expressions in our code. So let's do that. We are trying to maximize our equation, and let's give it a name of total profit. And for each element of products indexed by J, we multiply profit per ton of that indexed product by the amount of that product. And after that, we make a summation of all these results. And this will be our goal equation. After writing our goal equations, now it's time to write our constraint equations. Our first constraint is about total time per week. And to calculate this constraint, what we need to do is we need to multiply how many hours we need to produce 1 ton of that product with the amount of that product to be produced. And we will do this for each product, and we will take the summation of them, and the summation of them must be less than 40 hours. And as you can see, this equation looks really similar to our profit equation, so we can implement them in the same way. So let's do this. For each element in our set of products indexed by J, we need to multiply 1 divided by tons per hour parameter of that product with the amount of that product to be produced. And after that, we need to make a summation of all these results, and our final result should be less than 40 hours. And instead of using 40 hours here, we will use our parameter that we create for it, which is maximum production time per week. And we will put a semicolon, and this will finalize our first constraint. And our second constraint is about upper production limits of the products. Let's implement it also, and let's call it constraint upper limits. For each element in our set of products, each element should be bigger than 0, and each element should be smaller than their corresponding upper limit parameter. And semicolon. And as you see, we don't use summation for this constraint. The reason for this is that we want to compare each product's amount with their corresponding upper limits, one by one. And because of this, we do not need summation operation here. And after this, we are finished with our model. Okay, I made a mistake here. After finishing our model, we have to tell GLPK to solve it, and then we can use our displays. It should be like this. After our model part, we'll just kind of tell it to solve. And after this, we can start writing our display statements here. Let's say display part. Let's show X, and let's show our total profit value. Let's say we want to print each X variable. So what we need to do is for every element in our product set indexed by J, we have an X value. And with the help of our J indexing operator, we can print these individual values like that. After the display part, as we talked before, now it's time to put our data. So let's start putting our data by saying that we are starting our data part. And we can do something like this to make it more pretty. First, let's put our data to product set. So we'll just kind of say set products. And in GLPK, assignment syntax uses colon followed by equal sign. And we will just kind of say bands and white space and coils and semicolon. This means that our product set has two elements, bands and coils. Now time to fill the parameters. As you can see, we have 4 parameters and 3 of them are indexable parameters. So we must put the data such way that it must create a connection between the products and their parameters. So let's do that now. To make this connection, we will gonna create our parameters in matrix format with our data. So we have tons per hour, and then we have profit per ton, and we have upper limits. And let's do it like this to make it pretty. And then we will put our assignment sign. And our first line will be for our first product, which is bands. And tons per hour parameter for bands is 200. And profit per ton parameter for bands is $25. And upper limit is 6,000. And then we're gonna go to next line, and it's for coils. Tons per hour parameter for coils is 140, and profit per ton is $30, and upper limit for coils is 4,000. And we will finish this matrix statement by putting semicolon to the end of last line. And the last data we have to put is maximum production time per week parameter, and so let's put it in there. And we're just gonna put our assignment sign, and it will be 40 hours. And as we talked at the beginning, after finishing all, we have to put our end statements, and our code is ready. So let's try to run it and see if there are any mistakes. I'm holding Shift and right click and open PowerShell window here. Let's make it big. GLP sol -model lesson 1 G generalized.mod, and we have one error in line 17. Okay, because we forget semicolon here, it's giving us error in this line. So let's try to run it again. And our new error at line 31, let's check it out. Okay, in here we have to put colon after our indexing statement because we are not summarizing our results. So let's try it like that. And as you can see, optimal linear programming solution found, and we got the same values as the last time. And as you can see here, these outputs are generated by display statements, and these two are generated by our printf codes. Before adding new data to our program, I also want to mention some little variations in syntax which may be confusing for you if you don't know about them. First of all, we do not need to define or specify the indexing operator immediately unless we are making use of this indexing operator in that code line. So we do not need to include indexing operator here. And if we do it like this, it will have the same meaning as before. And we can do the same thing for these parameters because we are not using indexing operator immediately. So let's get rid of them. As you can see here, this J is being used by profit per ton parameter and X variable. So we cannot do the same thing in here. In this code line, we need to specify our indexing operator. Also, another variation you may encounter is instead of saying subject to, you can just say s.t. And this will be equal to subject to. And let's do it for also here. And let's rerun our code to see if anything changed or not. And as you can see, we have the same results as before. In our program, we made the model and data separation inside our code. And let's make the separation in file level. We can take our data part without taking the end code. Let's save it and let's create a new file here. And let's name it lesson1 g.file. And let's paste the data part here and let's save it. And as you can see in our model file, we do not have any data, and in our data file we have no idea what the model is. So let's run it again. To run our program from separated model and data files, all we have to do is specify data and model file names here. So let's say GLP sol -- model lesson1 g.mod and -- data lesson1 g.dot. And as you can see, optimal linear programming solution found with the same results from the last time. And as a last part of this video, we can demonstrate benefits of model and data separation by adding a new product or factory. Let's say our new product is steel plates, and profit per 1 ton parameter is $29, and time required to produce 1 ton of steel plates is 1 divided by 160 hours, and maximum limitation per week for steel plates is 3,500 pieces. To solve our updated problem, all we have to do is to change our data. So let's open our data file. And here, all we have to do is add another element to our products. Let's call it plates. And we need to add plates parameters to our matrix. Let's do that. So we will say here plates, and it is tons per hour parameter is 160 hours. Profit per ton is $29, and upper limit is 3,500 pieces. And let's save it. And now we can rerun our codes and see our results. As you can see, after adding a new product, our total profit value changed. And in this case, to achieve maximum profits, we need to produce 6,000 pieces of bands, 0 coils, and 1,600 pieces of plates.